I want to try some practice exercises involving linked lists, but I know I'm going to have to tread carefully because we've already done a bunch of linked list stuff in lectures, and frankly, it's pretty much the standard set of linked list exercises that we've already done, and also because I don't really want to step on our assignment materials. So I know from doing videos for 111 that there is a way of getting ChatGPT to sort of help me out as far as notation is concerned. So one thing I might do is give it some of the definitions that we've used in our lecture examples to avoid it going too far off the rails. But before that, I'm just going to try asking it for linked list exercises and see what it comes up with. I want some practice writing code for linked list. I'm going to say linked list operations, because maybe that way it's less likely to give me an exercise that's just, write the class for a linked list node. Can you generate a programming exercise involving a linked list operation where the exercise includes starter code with the definitions necessary to create the list? I misspelled definitions, fair enough. We'll see what it does. Don't show me the solution. Sure, okay, let's see what it comes up with. So write a C++ program to implement a singly linked list and perform the following operations. So basically what I want to avoid in this exercise is writing the entire list from scratch, because yes, that is good practice, but no, I don't need ChatGPT to tell me to try doing that. I want to do something interesting. I want it to suggest something I hadn't already thought of. So it's suggesting that I basically write a raw linked list, so not using shared pointers, but this is a valid node type given that. Insert at beginning search and display list. And maybe you can see what I meant at the beginning. These are things we've already done in the lectures, although I really like this business, the star ampersand happening with the head pointer there. That's a bit too basic. Can you generate some starter code which already contains basic list definitions and operations, but where one interesting operation in the form of a function is missing? Now, I'm going to acknowledge that in the last few videos, I have really been leaning hard on asking it for function-based exercises, which is a little bit, I don't know, there's a bias there because a lot of people that write programs have to write code in main. They actually have to write the test cases. The issue is it doesn't seem to be able to suggest very interesting exercises unless I give it a prompt like that. Otherwise, it just basically says, write this entire program from scratch. Basically, what it's asking me to do is to just reproduce lecture examples or something. Okay, so where one operation is missing, for the instead of the missing function, include a detailed header comment containing a formal specification. Don't show me the solution. Certainly. Okay, here's a more advanced exercise. Okay, so we still got this list. Now, what I would probably do if I did this exercise is I would change this regular pointer to be a smart pointer of some kind. There's my linked list class, insert at beginning, display list. Okay, so it hasn't really understood. For some reason today, it hasn't understood what I was wanting. It said, instead it's generated a template for a function header comment. That's sort of odd. Yeah, this is what I was afraid of. It's only suggesting basic exercises that we've all already done. This is stuff we've seen in labs and lectures, and I've got other videos for it. So let's shift gears and instead hand it my list definition and see if it can start with this and do something interesting. Here is, let's start over. Here's the definition for a list node. And I took this definition from one of the lecture examples. I think it was one of the ones involving using raw lists, so using recursive lists. Can you generate an exercise that involving performing some unusual operation on a linked list implemented with the definition above? Don't show me the solution. We'll just start with that. I'm not optimistic, to be honest. I think I'm going to have to ask it for a lot more clarification. So what I've noticed when I was recording videos for 111 is that ChatGPT does seem to be able to understand if I paste in definitions like this, and it does seem to be able, at least in C, to generate me exercises based on my own definitions. Okay, element manipulation, that's what it's calling this exercise. It looks like it's preserved the definition that I handed it, so that's fine. We've got display list. It's written its own display list function that to me looks pretty much correct. And then what's my exercise? My exercise, I see. Okay, I don't really understand what the deal is here, but I'm just going to copy this and stare at it. Okay, so the exercise is showing up in main, and it looks like it's gotten confused again. So it says it's decided that it doesn't know what an unusual operation is, so it's told me, go and perform an unusual operation. The function, write a function in the middle of main that performs an unusual operation. The function should perform a unique operation on the elements in the linked list. You need to traverse the linked list and apply this operation. So it gives an example. The operation, so if your list is 1, 2, 3, after performing the operation, the list might become 2, 4, 6. It doesn't give me an actual task to do. It just says make one up. It should modify the element in a unique way, doubling it, reversing digits. Okay. No, sorry, you're not doing what I want. I don't want to think of my own unusual operation. Please design an exercise for me. Maybe the way I stated the problem, it didn't understand what I wanted. I don't know. It seems like it's gotten stuck in a rut today where it just generates these templates for things. The transformation should be multiply each element by 10. Okay, well, we'll try this. So we'll copy this. We'll go and replace the earlier template with this. So what do we have? We've got my node definition from earlier, okay? There's this display list function. That's nice. ChatGPT, when you ask it to create a list, I've noticed this in the 111 videos, it seems to just want to make a bunch of nodes as variables and chain them all together. And then we call display list. Okay, fair enough. Now, it gives me a task to implement a function just buried in the middle of main here. So I guess I'm going to grab this weird specification and just bring it up here and then write a function. Because, you know, if I'm writing a function, I need to put it somewhere where it's going to compile. There we go. It's called transformElements. And it takes the head pointer to the list, and then it traverses the list and applies the transformation to each element. The transformation should be multiply each element by 10. Okay, that isn't that exciting, but it's doing the best that it can. So we'll call transformElements here. We'll try and give it the benefit of the doubt. TransformElements, and I give it the head pointer. So when I pass in the head pointer, it seems to me as if all I'm modifying are the elements of the list. So if I make a function transformElements, and I take node ptr head, the structure of the list is not going to change. So there's no situation where I can imagine I'm going to need to modify the head pointer as a result of this transformation. So I'm just taking the head pointer by value. I'm not using an ampersand here. And now I want to loop over the list. Okay, so node ptr node equals head. Node is not equal to a null pointer, and then node equals node arrow next. And then it looks like all I need to do here is go and grab the value in the node. That would be element, and then multiply it by 10, which, I mean, I'm happy to oblige, but that's not quite an unusual exercise in my mind. So multiplied by equals 10. And then I think that's it. Okay, so let's run it. Great, I've done the first linked list exercise. What other tests should I do here? Let's see what happens if I'm just going to doctor the list that it created to set the next pointer of the head element to be null. So that means that there should only be one element in the list. It's always good to try out even basic operations like this on... yeah, so it still works. That doesn't surprise me at all. I think I'm going to call this exercise done. This is way too basic for what I was hoping it would give me, but I've now done this exercise, so I can tell it I did it and I can try and move on. That was nice. I'm going to ask it for another exercise. I'm worried that it seems to already have gotten stuck in this mindset of generating these weird function templates in the middle of main. And if I ask it for another one, it might do that again. Can you generate another exercise that is way more challenging? Now, I might regret this, but I'd rather regret it than be bored. Advanced linked list operation, element rearrangement. Okay, that sounds exciting. So I've got my linked list definition from earlier. There's display list. It's constructing its own homemade list of size 4, and then it just sort of jammed the specification for the exercise into the middle of main, which is sort of annoying. Okay, but it looks like there is a valid exercise here, and it does, skimming over it, it does look like it could be pretty challenging. So let's grab this and head back over here. And really, in the last few videos, I have noticed that we are sort of hitting ChatGPT's limits in some sense. It seems like ChatGPT is much less able to understand what I want and to generate it. And even when I give it a really long explanation, it still can't quite figure out what I want in some cases, and it doesn't generate everything. So in the last few videos, it's often when I said, give me test cases in main, it just puts a comment in main saying, here's where you put test cases. I think that's because we're getting to topics that are complicated enough that it can't quite wrap its head around them, so to speak. Whereas in 111, for C exercises, it was usually a step ahead of me. It was able to generate pretty complicated exercises. Okay, so we've got the same pattern we had before. I will stop, I'll just pause here to note that this display list function that it's written doesn't look like what I would write, although it's 100% correct. So it doesn't use C, it uses C-style initialization. We all know that that's something that annoys me. But it also likes to use this while current, as opposed to while current is not equal to null, which to be honest is probably what I would write too if I weren't teaching C++. I like the not equal to null comparison because once you get into the habit of writing it, it makes the code a lot more readable. Okay, I'm going to grab this. And it does look as if this operation is non-trivial, so I'm happy about that. I'm going to just delete this boilerplate here and just write in rearrange elements. And from what I was able to see, so I'll paste in the specification here. This doesn't really look like any of the function specifications it's generated in the past, but I mean, it's something. So it looks like rearrange elements is going to alter the structure of the list, or I guess depending on how I do it, it could alter the structure of the list. If the original list begins with 1, this rearranged list begins with 2, and the 1 has been moved. So I guess that means I could modify the head pointer. Now, of course, I could also leave all of the nodes of the list in place and just shuffle the elements around. But because I might modify the head pointer, I suppose that when I implement rearrange elements, I'm going to design it so that it takes the head pointer by reference so that I could modify it if I want to. All right, so void rearrange elements, and then it takes node ptr head. But it takes that by reference so that I have the freedom to modify that if I want to. Okay, so what am I supposed to do? This function is just called rearrange elements, and it doesn't give any indication of what that means, but the details do clarify it. So we've got this list that contains integer values that I guess are either odd or even, okay? And I'm gonna move all of the even elements to the beginning of the list in their original order, and the odd elements to the end. And then I maintain the order of even and odd elements among those groups. So if 2 comes before 4 in the original list, then 2 comes before 4 in the result. Okay, it's weird how we got to this point, and the specification is a little bit sort of, it doesn't quite make perfect sense. But actually, now that I know the exercise, this is actually a really good exercise. This is the kind of thing that I'm usually straining to come up with when I'm writing exam questions. So it did come up with a good exercise, although it came up with it in a very odd format compared to what it usually does. How will I solve this? Okay, so I'm going to think about it like this. You give me a list that contains a bunch of elements, and they can be either even or odd, and they have to be even or odd. Even negative numbers are going to be even or odd. Okay, so there's 6, 10, 17, and then 1, well, actually, let's put 187 here, and then we'll put 6 at the end. So what I want is to generate, when I'm done, I want to have a list where it has the even elements first, but in the same order they were originally in. So it should be 10, and then it should be 6, and then it should be 187, and then it should be 17. Now, there are a lot of ways to try and parse an exercise like this. It doesn't say, so if this were one of our exam questions, we need to take note of restrictions it doesn't impose. It doesn't actually say that I'm not allowed to use vectors, for example, or that I'm not allowed to use any particular like design methodology, like I have to use recursion or I'm not allowed to use recursion or something. So keep that in mind. If the exercise doesn't say I can't do something, then I can. So in this case, what I could do, and this would be phoning it in a bit, but it would probably be valid in an exam context unless you were told otherwise. I could just put all the elements in a vector, fiddle around with them, and then dump them back into a list. I'm not going to do that because it feels like that's sort of exploiting a loophole. What it also doesn't say, and this would be fair game, is it doesn't say that you're not allowed to create a new list. So that is, it doesn't say that you have to simply rearrange the pointers of these nodes. I can make as many new nodes as I want. So one valid technique here would be to just create create a brand new list that has everything I want in it. So I think I'm going to start with that, but I don't want that to be my final solution. I feel like I could do better than that. Creating a new list isn't a problem in general, right? You often need extra data to get stuff done when you're writing code. However, if this list had size 1 billion, and I have to make a new list also with 1 billion elements, then yeah, that could end up putting me into rough territory. So finding a way of just rearranging elements, if possible, without creating new nodes or creating too many new nodes is a good idea. But I'm going to start by doing this what I consider to be the basic way, which is what I'm going to do is I'm going to make a new list. So I'm going to say make a new called new head equals null pointer. And now what I'm going to do is I'm going to loop over my original list and grab all of the even elements and then add them to my new list. And then I'm going to loop over my original list and grab all of the odd elements and add them to my new list. And that's it. Now, do I have a function to insert at the end? I've got display list. Oh, I don't have a function to insert at the end. Okay. I guess I'd have to write that function to make this work. Now, that does change, I guess, whether this is a good idea or not. I'm going to do that, though. Let's write a function to insert at the end of the list. I sort of have to be creative and imagine my own exercise here because ChatGPT doesn't seem to have that many ideas. Insert at end, and it takes node ptr head. Now, I could write this either in a recursive way or in an iterative way. I think it's easier to do iterative given the signature I've already written. So I'm going to go find the last node in the list, and I'm going to start that at head. So I'm also going to observe that there are two cases for inserting at the end. If the head pointer is null, and actually, if I'm inserting at the end, I may still need to modify the head pointer. If the head pointer is null, well, in that case, the list is empty. So I'm inserting at the end is basically the same as inserting at the beginning. So I'm going to do make shared of node, and I'm going to say the next pointer of that new node is going to be null because it's at the end of the list. And then the element, inserted end has to take an element as well. So I'm going to say int value. And the element is just going to be the value I was provided, and that's it. Otherwise, so if the list is not empty, I'm going quickly through this because you've seen me do this in a different video. If the list is not empty, then I'm just going to go find the last node. So the last node would be a node with the property that the next pointer of that node equals null. So while last node arrow next is not equal to null, then I'm not at the last node. And so we will just iterate along. Last node arrow next equals, last node equals last node arrow next. And then when I'm finally get to the last node, and I know if I get to line 27, there will be a last node. The list has at least one node, so there will be a last node, so I will find a last node. Last node arrow next equals, and then I create the same new node I would have created above. I stick the value you gave me in a new node. The new node's next pointer equals null. All right, so that's inserted end, and I'm thinking that I probably should test that somewhere. I'm going to try and just write this because I feel like if you see what I'm going to do, if it doesn't work, then I'll write some tests for inserted end. What I'm going to do with rearrange elements now is I realize that what I want is the even elements in the original list, then the odd elements in the original list. I could get this effect by just walking through the original list, looking at every element. If it's even, I add it to my new list, and then I stop. And then I iterate over the list again, and I say do the same thing, but only keep the odd nodes. So I end up with all the nodes in the right order. So I'm going to iterate over my original list, node ptr node equals starts at head, and then node is not equal to null ptr, and then node equals node arrow next. Okay, And then I'll just ask the question, if the element in this node is even, then I keep it. So if node arrow element mod 2 equals 0, well, that means the element is an even number. In that case, I'll call insert at end. I'll insert into my new list, so I give it the new head pointer, and I give it node arrow element. And then I'm just going to copy and paste this entire loop and run it again, except I'm going to do odd instead of even. And when I'm done, I have this brand new list with brand new nodes. I've made a copy of all of my nodes, and it contains the elements that I want. So what I do is I just take my old head pointer and I redirect it to point down here. Now, doing this will result in all of these nodes being destroyed, as they should be, because otherwise we'd have a memory leak, and that's the magic of shared pointers at work. So that's what I expect to happen. So I'm going to write head equals new head. I'm just going to point my old list to be my new list. So this was creating a copy of every node. And I mean, also to be sure, the inserted end function, calling it over and over again is going to take a lot more time than I otherwise would need. This is a bit of a sloppy solution in that sense. For an exam, this would do the trick if you are allowed to create new nodes, and you're allowed to write the insert at end function. But every time I call insert at end, it has to walk all the way to the end of the new list, and that means that I'm doing a lot of wandering through lists because I have to start again from scratch every single time. There are faster ways to do repeated insertions at end, but I guess me writing it this way is a testament to how little you have to care about that in an exam exercise. It doesn't require you to handle that case. Let's see if this compiles. Looks like it does. We'll try running it, and it doesn't look like it worked. Looks like, oh, right, it didn't compile. Okay, so the compile command I ran was for the last exercise. So I want to do practice linked lists 2, not practice linked lists 1. Okay, that's still compiled, and now I run it, and it does look as if there are the even elements and there are the odd elements. I'm going to take this as an assurance that my inserted end function worked. Now I'm thinking about how best to continue testing this. So now that I have an inserted end function, maybe I should delete all of ChatGPT's built-in test cases and just write my own. So I'll say, okay, create a head, we'll make that null PTR, and then I'm just going to do insert at end to add elements. So insert at end from head, let's do 6, or we'll create the same list I have over there on the right. So 187, there's 10, there's 17, there's 6. Okay, this is another list of size 4. Okay, and there are the even elements and there are the odd elements. Let's add more things. So we'll do 111, we'll do 445. Let's make sure we can it still handles having 2 odd elements in a row. Let's do a negative number, -1, that's also odd, and let's finally do 0. Okay, so we'll try running that. And it looks like that works. Yeah, that solution is correct. Now, is this really a good solution? I would say no. This is sloppy in a couple of ways. So one of the ways it's sloppy is we're creating a copy of the list. And we don't need to do that, I think. Maybe we do, but I don't think we do. One of the ways it's sloppy is that we have this copy of the list. And so if the list has size 1 billion, then we're using a huge amount of memory to perform an operation that seems to only require rearrangement. Okay, the other problem is insert at end is pretty inefficient in this context because every time I want to add an element to my new list, I call insert at end, which walks along from the beginning all the way to the end. And that's obviously not necessary because I could just be keeping track of the last node in my new list as I run along. Insert at end is designed to be called, from scratch, so without any knowledge of what you already know. But because it's walking along like this, it actually is going to be pretty slow. In particular, if the new list has n elements in it, then insert at end requires n operations. I have to actually walk through all n elements of my list. That means if I call insert at end and I want to insert n elements over time, well, the first time I call it, it takes 1 operation. It just inserts at the beginning. The second time I call it, it takes 2 operations. It skips over the first element and then inserts after that. Then it takes 3 operations on the third element, then 4. And if we think about this, we actually end up with this sum here. This is the number of operations it takes. 1 plus 2 plus 3 plus 4 all the way up to n. And it turns out that that number is equal to this, n times n plus 1 all over 2. Which is equal, just to be really clear about this, it's n squared plus n, which means that I'm adding n elements to my list. There are only n things that I'm working with, but the number of operations I'm doing is n squared, and that's going to obviously get pretty slow as time goes by. The more elements I'm inserting, n squared is going to get larger and larger much more quickly than n is. This rate of growth is, of course, quadratic, so that's a problem. And so maybe I can do better than that. Okay, let's see what we can do here. Okay, we'll just painstakingly erase this part of the diagram because I want to keep my list. I think a full solution, I think creating the copy and calling insert at end are two separate issues. If I had a better version of insert at end that didn't have to walk all the way to the end from the beginning at each step, then I could end up with an implementation that was a great deal faster. And actually, you know what? We're talking about speed. Let's see if we can, I'm wondering whether it's worth it to try and create a test case where I'm making a list of like 20,000 items. I guess it wouldn't make any sense because we can't print it out. I mean, to debug this, we sort of have to look at the output. So I'll leave that. However, you might consider taking a look at this code and see what happens if you create a list using insert at end with 50,000 elements. You'll discover that it's going to take a really, really long time, way longer than it should normally take for that purpose. So what I'm going to do is skip directly to what I think is a better solution, or a solution that is more efficient and a bit cleaner. And it works like this, basically. So here's my original list. This is the list that I want, this thing at the bottom. Okay, how am I going to get it? What I'm going to do is I'm going to take this list up here and I'm going to divide it up into two pieces. I'm going to divide it up into the even version and the odd version. And the even version and odd version will be two completely separate, completely empty lists, the completely brand new lists. As I go through my original list, I'm going to grab each node and move it to be in one of my two lists. So the 187, I'm going to grab it and put it over here. The 10, I'm going to grab it and put it here. And then the 17 goes at the end of the odd list, and the 6 goes at the end of the even list. So you can sort of see what I'm up to here. And then when I'm done, I'm just going to attach the end of my even list to the beginning of my odd list, and then redirect the original head pointer to point to my even list. So I will not have created any new nodes. I will just have gone through and tossed each node in a bucket based on whether it was even or odd, and then stitched together what I come up with at the end. Now, there's a lot going on here. So I'm going to probably have to go through a couple of iterations to make this work. So what I'm observing is first that if I have this even list, then as time goes by, it's going to have lots of stuff in it. So there's 10, there's 6. If I want to stick a new node at the end of the even list, I better keep track of what the last node in the even list is. Because if I don't know what the last node is, and every time I want to add a new node, I have to walk along starting at the beginning, which is something I just said I'd rather avoid. So for the even list, I'll have to keep track of the beginning of the even list, the first node, and the last node. Now, keeping track of the last node in a list is not actually a big deal unless you're doing more complicated manipulations. So for singly linked lists, keeping track of the last node can be a bit of a bookkeeping nightmare if you have lots of different manipulations. But I'm not doing that here. I'm just building a list from left to right. So I'm going to make 2 pointers for my even list and 2 pointers for my odd list. Even head, and that's going to be null PTR. Okay, I'm just going to pretend I didn't see this C-style initialization I've written here. In fact, why don't we just delete all of this? And then I'll do node PTR even tail null PTR. So it's going to be last node in the even list. And then I do the same thing for the odd list. Odd head and odd tail, and that's the last node in the odd list. Now I'm going to have to remember that if odd tail is equal to null, that means the odd list is empty. Now I'm going to write a loop that iterates through the original list. So I'm going to say, let's see, for node PTR node, and that starts at head. And then node is not equal to null pointer, node equals node arrow next. And what do I do at each step? So what's going to happen is I'm using this loop to walk through my original list, but as I go, I am going to dismantle my original list. So at each step, I take the node that I'm currently working with, and I just break it off from the list. And and actually, I'm going to have to adjust. I'm going to write a while loop, not a for loop for this. I'm going to rewrite this. So I'm going to say, the reason I need a while loop will become clear in a minute. I could use a for loop, but it won't make my life much easier to do so. So I'm going to say while node is not equal to null pointer. And then this is my incrementation that I want to eventually do, but there'll be a special case. So node equals node arrow next is what I sort of want to accomplish. But here's my idea. I've got this pointer, so there's the original head pointer. And this is going to be basically decommissioned. The minute this loop starts, the original head pointer is going to become useless. I'm going to have to make sure I never use it again until I'm done this function. So what I do is I've got a pointer to one node. What I'm going to do now is I'm going to break that node off, and that means the node is going to become part of something else. So the node is going to become part of my odd list. So I'm actually going to take this node and arrange it so that basically my odd list starts with this node. I'm going to add the node directly to the odd list. I'm not going to create a new node. I'm just going to move this node into a new list. The issue is I still have to keep track of what else is in my original list. So I'm going to call this next node. It's going to be the next node of the original list that I'm going to work with eventually. And I'm going to save a pointer to that right now. Node pointer next node gets set initially to node arrow next. And then when I'm ready to wrap around to the next iteration of the loop, I'm going to set node to be next node. Because node arrow next, I'm going to manipulate that in the middle. So next node is going to keep track of the node in the original list that I'm going to look at next. And now I am free to take the current node, that's the one labeled node, and move it around, put it inside some new list. So now I'm going to ask which list I'm putting it into. So if node arrow element mod 2 is equal to 0, then it's even, otherwise it's odd. Here we go. Okay, so in this case, I'm going to add node to the even list. And down here, I'm going to add node to the odd list. Okay, how do I do that? Well, I have two cases. So the two cases are and we can actually see them reflected in this diagram here. We've got our even list that already has something in it, and we've got our odd list that is empty. So in either situation, the even list or the odd list, you could have either case. So if even head is equal to a null pointer, well, that means the even list is empty. So this is adding the first element to the even list. Otherwise, we're adding a subsequent element. So I'm just going to remind myself of that, adding the first element to the even list. Otherwise, adding another element, adding the second or greater element. So how do I add the first element to the even list? Well, that looks pretty easy. I set even head to equal my node. And then I set even tail to equal my node, because this is going to be the first and only element in the list. And also, I set node arrow next to equal a null pointer. I'm going to redraw my diagram so that this is more, I feel like there's a way of diagramming this that I could do if I had a board, but it's pretty hard on screen. So here are my two lists. I've got my even list, I've got my odd list. And then here's my original list. We'll just say this is my head pointer from my original list. And so I've got, there's the first node, there's the second node, and so on. So at each step, I've got node positioned here. So let's say at the 6. And I've also got next node. And it's positioned at the next node over in the chain. Now, what I do is I say, is the node's element even or odd? It's even. So then I want to actually move this node into the even list. So I do that. This head pointer becomes irrelevant. I'm just going to who knows what the head pointer equals to at this point. I mean, it's going to still point to what was previously the beginning of the list, but we're no longer going to use it. We're going to pretend we don't see it. Once the loop is started and I'm walking along the chain, the head pointer becomes irrelevant. Now what I do is I set the even head to point to this node here, this 6. I'm just going to move the node upwards a little bit to make that more obvious. So the 6 is now part of my even list. Now, because my even list is supposed to be a list and the only thing in it is the 6, I want the next pointer to be equal to null, because I want my even list to be a proper list, not just sort of a different on-ramp onto my original list. And you can see now that because node arrow next is now equal to null, my node pointer can't be used to continue the loop. But fortunately, next node was there all along, keeping track of the next element the next node that I want to work with. Okay, so let's suppose, this is the first iteration of my loop. Now, let's suppose we get to the next iteration of the loop and we're also looking at an even number, because that lets us talk about the case on line 72. So on line 72, we've got node is now pointing to this thing, and next node is now pointing to the 17. So what do I want to do here? Well, what I want to do is this is the head pointer for the even list. So that's even, okay, that looks stupid. That's even head. And then even tail is also a pointer that tells us the last node in the list. And of course, in this case, the list only has one thing, so even head and even tail are the same thing. So what I want to do is I want to take my current node, that's the 10, I want to stitch it in to my list. So here's the 10, I'm just taking the node and moving it up here. So I go to look at the previous element of the list, that would be the tail of my even list, the last element. I set its next pointer to point to the 10. I set the 10's next pointer to be null, and then I want to set the tail of my even list to be the node that I just added. Okay, so we can write that in. So I'd say we don't care about even head in this case. So I'll write even tail arrow next equals node, and then node arrow next equals null pointer, and then also even tail equals node. And so I've modified to actually do the modification to the list. That would be these two modifications here. Something points into my node points out to something. In this case, nothing, but it has a pointer that points to the next node or lack thereof. Even tail equals null ensures, or even tail equals node ensures that at the next iteration, I still know what the last element of my even list is. And I think that's it. I mean, the odd case is basically the same, except I say odd instead of even. So I'm going to copy this. I'm going to jam it down here. And then I've got, so if odd head, and then we'll just paste this in, and then odd tail, and then I'll change these words to be the word odd. So then we've got odd tail, that's this. I think I've changed everything I have to change. And then what happens when I'm done? So when I'm done, I've got these two lists. I've got the even list and I've got the odd list. And so the even list would be 6 and then 10. And then the odd list would be 17 and 187. And both lists are real lists. They have a real end to the list. What I want now is, keep in mind, of course, that I do have the tail pointer that tells me the end of each list. What I need now is a list with all the even elements first and then the odd elements. So what I'll do is I'll take the head pointer to my original list and I'll redirect it to point to the beginning of the even list. So that's down. So here's my loop to, so scroll down a bit. Here is the end of the loop that iterates over the list and separates them into even and odd. Now I set the head pointer to point to the beginning of the even list, the first node in my even list, and then I'm going to stitch the end of my even list to the beginning of my odd list. I'm going to take the tail pointer of the even list, so even tail arrow next equals odd head. And I'm going to come back to that in a minute. There's one special case there. So that would be this. And you can see, if I now walk along the list from the original head pointer, I get all the even elements, then all the odd elements. I'm going to write, come back to this, something bad could happen. There's something I want to handle on line 97, but I want to test out what I have in the meantime. All right, let's see what we have. So we should get 10, 6, let's see, 10, 6, 0. I just noticed something strange, which is in the previous version, there was a mistake. I just didn't notice it. I was overconfident. The -1 wasn't properly added to my list last time. I think that was a bug to do with my use of the modulo operator, but it's too late now. The issue is when you use the modulo operator on negative numbers, the result's going to come out to be negative because it doesn't work the way modular arithmetic does in a number theory course. I apologize, but I can't fix the bug that I had 20 minutes ago because it's been 20 minutes. However, I'm pleased to say that it appears as if that bug is gone. My new implementation doesn't have that problem. So here's the list. I should get 10, then 6, then 0, which I do, followed by 187, 17, 111, 445, -1. This looks like a correct implementation. And although there's quite a bit more code, I mean, clearly, but the code isn't that much more complicated, just tedious. This code doesn't create any copies, and it doesn't waste any time on iteration that it doesn't have to. And I really like, and this is a personal bias, so in my own algorithms background, I just grew to like this. I really like that we've got one loop. I'm a big fan of writing one loop to walk through sequences from left to right. I would much rather have one loop that goes from left to right and more complicated logic inside the loop than have nested loops. And so that's what I have here. I have one loop, I grab each node, I put it in either the even list or the odd list, and then when I'm done with a couple of simple operations that don't involve loops, I just stitch those two lists together. Let's try a couple more tests of this. So let's try adding a few more elements. Actually, let's add some odd and even negative numbers. So there's -3, and then we'll do negative 17. And we've got, let's see, 187, 10, or we should have 10, 6, 0, -2. Yep, those are the even numbers. And then 187, 17, 111, 445, -1, -3, -17. Yep, I think this is correct. Let's see what happens. Now, there is that case I said to come back to. Come back to line 97. Something bad could happen. Before I tell you what bad thing I think could happen, I'm going to see if I can show you. I'm going to comment out a few of the test cases. And maybe you'll see a pattern in which ones I've chosen to. So these are elements that are no longer going to be part of the list. And then we'll see what happens here. And something bad happens, seg fault. So what's the deal? Well, the issue is, well, I guess there are a couple of things I have to deal with. The issue here is that there are no even elements. So when I'm done, and you can see here, all of these are odd numbers. So when I'm done my segmentation that I performed in my code, I've got this odd list that has a bunch of stuff in it. So I mean, we can't see that in the test case, but I'm pretty convinced it worked. The odd list does have what we want in it. Everything we expect to be in there is in there. The issue is, because the even list is empty, this modification, this modification that I'm doing on line 98 is going to cause me some trouble. So I've got my odd list, I've got my even list, and I've got my head pointer to my original list as well. So I say, okay, so here's the even list, it's empty. So even head is equal to null. I set my head pointer to be the same as the head of the even list, which is now equal to null. So my result list is now empty. That's already a problem. But then I do something unforgivable. On line 98, I say even tail arrow next equals odd head. So the problem with that is that even tail, because the even list is empty, even tail is a null pointer. I'm not allowed to do arrow next on a null pointer. And so, of course, that crashes the program. So I need to handle this situation. Now, how did I catch this? I mean, you saw that I added a note here to come back to it. What I'm doing when I work with pointers, especially data structures that have these like next pointers, is whenever I use an arrow, I have to, in the back of my head, I'm thinking, am I guaranteed that the thing on the left is not null? Always. Whenever I use an arrow, I think, have I tested that? So an example here is I use an arrow in this loop to do node arrow element or node arrow next. When I'm writing code like this, I'm always thinking, do I know that node is not equal to null? And in this case, I do, because the loop only runs when node is not equal to null. Once I know that node is not equal to null, this is safe. This is 100% safe unless I've modified node somehow. So I'm always trying to contemplate, is the thing I'm using on the left of the arrow guaranteed to be non-null? If not, then I need to think about that. And I noticed when I was writing this line that something didn't feel right about this line. So here I'm going to say, I think the special case is when even head is equal to the null pointer. So I'm going to first get rid of the crash, and then that isn't going to fix the bug. That's just going to delay the bug. It's going to push the issue forward to when the program runs and when we see the output. So if I run this, it still crashes. Okay, what have I? That's peculiar. If even head equals null pointer, it could though be that the crash is happening somewhere I'm not expecting it to. Okay, so maybe I'll complete my fix. Maybe if I do this in an incomplete way. So basically, if the even list is empty, then what I should be doing is saying, okay, so if even head is equal to a null pointer, then what do I do? Well, then what I should do here is I actually handle this separately. If there is no even list, then the head pointer should just point directly to the head of the odd list, and that's the end of that. There is no even list, so don't try and splice it in. Now, otherwise, I should do what I was already doing. So head points to the even list, and even tail, arrow next, points to the beginning of the odd list. So here, I haven't directly checked that even tail is not equal to null, but I can reasonably assume that it isn't, because if even head is not equal to a null pointer, then there is at least one node in the list. And if my logic up here is correct, then I expect if there's at least one node in the list, the tail pointer should be valid. You could say, but what if your logic is invalid? Like, what if the even tail is null and even head is not? Well, if that's the case, this is going to crash, but I deserve it because I'm making assumptions about the way my code works. If my code doesn't work the way I think it does, I have to fix it anyway. So if my code is otherwise correct, this is a valid assumption. Even tail should be non-null as long as even head is non-null. And I could use an assert statement there to make sure that I'm not beside myself, that I'm making a valid assumption. We'll try compiling this. We'll try running it. It doesn't crash. It's unclear to me why it crashed when I was trying to demonstrate my halfway done solution, but fair enough. The solution was halfway done. So here I've got a list with only odd elements, and we can see that it does still work. It's falling into this case, and I can prove it. We'll say there's case 2. Or actually, sorry, it's falling into the new case, which is actually up above. So, and here's case 1. So I believe that in the situation where the list has only odd elements, we fall into case number 1. And it looks like we do. Okay. Now, I'm going to bring back, obviously this modification could have broken something else. I'm going to bring back all of those missing test cases. Let's start by bringing back just one even number. What happens if the even list has size 1? It looks like it still works. Okay, what happens if the even list is full size, but let's say the odd list is empty? So we'll start with our original test case. Okay, that's still working. So I see all of the even numbers there, then all of the odd numbers. Now let's see what happens if the odd list has size 1. So we'll get rid of all of the other odd elements. I think there's 2 more. Okay, so we'll run this again. When the odd list has size 1, it works. What if the odd list is empty? So we would expect that it just gives us the even elements and doesn't crash. And it looks like that worked too. And then finally, one last test case. What happens if the list is only got 1 element? I mean, I think this should work, but we need to make sure we test it. Okay, looks like that works. And I guess one last one. I always forget this one. We should do this. What happens if the list is empty to begin with? Okay, looks like that works as well. So I had to do a bit of debugging there, and this is a bit of a tough case. If this were an exam question, I mean, that's a bit of a long exam question. If you choose to do it this way, we already saw there were easier ways of doing it. If this were an exam question, then I would expect that the difference between a 3 out of 5 and a 5 out of 5 is catching logic like this. Now, remember that depending on how you solve the question, whether you need to do this, or how it has to work could differ. So with my original solution that involved inserted and, I didn't need this weird special case. But it's my decision. So when I answer the question on an exam, it's true I could generate a really complicated, convoluted solution and lose a bunch of marks because I forget a special case. Whereas somebody that chose a simple solution doesn't lose those marks because they don't need a special case, whether they forgot it or not. And that's a case of maybe life's not fair, but it's also a case of having to take responsibility for your design. If you choose to do a complicated solution, then you take responsibility for the complicated solution working. Being able to identify a simple solution doesn't just give you the benefit of taking less time to write the code, but it also gives you the benefit of needing to cover less special cases. And that's something that every programmer has to be responsible for. Okay, so I'm done my rearrange elements exercise. I'm going to ask it for one more and hold my breath. Maybe it gives me something interesting. That was interesting. I have another exercise in that is similarly interesting, using the same format. So although I think the format it's given us today is weird, I have been able to work with it. Certainly, okay, element grouping. Now if this is what I think it is, this is a very nice way of following up on that last exercise. So there's display list. It's going to give me a specification. Okay, so I'll wait for it to finish and I'll just copy this right into my template. So copy code, head back over here, just put it right there. And then I'm going to do the same thing I did before, which is that, oh, no, it's too bad. So I was hoping that when it said element grouping, it meant group together all the occurrences of the number 2 or something like that. But it doesn't say that. It just says group all the even elements together and then group all the odd elements together. That is our previous problem. Maybe when I said similarly, maybe it took me a bit too literally. That is just the previous exercise. but rephrased. Try again. I apologize. Yeah, I'll bet you do. Now it's saying element partition, and I'm beginning to wonder because that seems like that's going to be, there's a decent chance that's the same thing. So what do we get? Oh, okay, this is interesting. This is what's interesting about this, if it is what I think it is that it's similar to, it's something you'd need in a second year course to write an algorithm called Quicksort, I think. It wouldn't surprise me if that's what this is supposed to be. So that's fair enough. Let's do that. So partition elements. And I'll put this up here. It doesn't give me any idea for how I'm supposed to call it, like what test case I should use, but it does give me a sample input, so I will use that. I guess that's the call I want to write. Okay, so partition elements. The idea behind partition elements is you take the head pointer to a list and then some integer value to use as the partition pivot. The function should then rearrange the elements so that all elements less than the pivot show up before all of the elements greater than the pivot. And so here, if we look at this list 58362, and I give you a pivot of 4, you're going to make me a new list where all of the elements that are less than 4 occur first, and all of the elements that are greater than 4 occur afterwards. So we get 32586. This is fundamentally pretty much the same as the last exercise, frankly, but it's an interesting reinterpretation of it, and so I do want to try it out. So now I'm going to call partition elements here. I'm going to start by actually using the same thing it suggests. So I'm going to call it with the list I have and the pivot value of 4. So I do head and then 4, because it looks like it's constructed this list as its fixed test case. So void partition elements, and that's going to be, it's going to take node ptr head, and it's going to take it by reference because it might change it, and then int pivot. And then what I'm going to do is shamelessly steal all of my code from the previous exercise, because frankly this is the same exercise but with a different condition. So I'm going to do a little bit of renaming, but that's pretty much it. So I'm going to also split the list up. My original list is going to get split into 2 pieces, the less than piece and the greater than piece, although this should be greater than or equal to, I think. Yeah, so what I'm doing is splitting my list into the subset, the sublist of things that are less than the pivot, and then the complementary sublist is the things that are greater than or equal to the pivot. So I'm just going to call that less and greater, but understand that I mean greater than or equal to. So less head, we'll just get rid of this. Oh, actually even better. So we'll do odd or even. I'm going to go back. I'm just going to use Control F. So Control H, okay, it doesn't. Edit, can I do a search and replace? Apparently, yes, I can. Okay, I can't do a replace, really? It does find but not replace. Oh, there we go. Okay, I'm going to replace all instances of the word even with the word, the even list went first, so that's less. Okay, replace all. And then I'll replace all occurrence of the word odd with the word greater than. Or we'll do GEQ for greater than or equal to. There we go. Okay, so I've just adapted my exercise. All I need to do now is to say if the node's element is less than the pivot, I add the node to the less list. And if the node, otherwise it's greater than or equal to, so I add it to the GEQ list. And I'm actually going to, after literally nothing but copying and pasting and doing a search and replace, I'm going to see what happens if I run this. And there we go. Okay, so it did the partition, and that shouldn't surprise us because that was basically just the previous exercise. What I want to do now is I want to bring in my insert at end function from before, and I want to try it out on the test cases on some of the test lists that I was using in exercise 2. So there's insert at end. I'm now going to go grab the insert at end, those calls to insert at end that I wrote myself to replace ChatGPT's. To replace its test cases. There we go. And then I'll uncomment all of this. All right, so we'll try running it on this. The pivot is still going to be 4, but that still gives us an interesting test case. So the pivot is 4, and we can see we've got a mixture of values greater than, well, they're already a bit skewed. Let's use a pivot of 50. So all the values less than 50 come first, then all the values greater than 50. Okay, and then let's also try what happens if we use a pivot that actually equals one of our elements. Let's use a pivot of 17. So I expect 17 to now show up at the beginning of the list of things that are greater than or equal to. And we can see, I have to compile it again. We can see that that doesn't look like it worked properly. So my pivot was 17, and then oh no, actually that makes sense. So I don't expect 17 to show up at the beginning of the list. I just expect that it's in the list of things that are greater than or equal to. By the same logic as in this example here, if I chose my pivot to be, this isn't a very convenient example for this purpose. If I chose, it's annoying. Okay, let's swap 6 and 5. So in this case, if I were to choose my pivot to be 6 or to be 5, then I would still expect to see this list come out. Because what I want is to add the pivot to the set of things that are greater than or equal to the pivot value. It doesn't have to be first, it just has to be in that second sublist. So yeah, what I have is correct. Now, the reason that I thought this was a neat exercise, so I think that's our exercise. The exercise is now done. The exercise was fundamentally pretty much identical to the last one, except that I changed other than the renaming of variables, I changed one line. It was the same thing. The reason why I thought it was sort of neat was that this partition idea can be used to create a sorting algorithm. So the exercise is done. This is the end of the exercise. If you don't want to see anything but the exercise, then you can now stop watching the video. I'm not going to ask ChatGPT for more exercises because it seems like it only has this one to suggest. It keeps suggesting variants of this one. So I think we've used up its creativity for this morning. However, I want to try a little experiment here. So I'm going to comment out my call to partition elements, and I'm going to write a new function. I'm going to call this function, So I'm going to write two new functions. Actually, I'm going to say split by pivot, and it's going to take node ptr head. And I'm going to say node ptr, what's the best way to do this? Node ptr, no, I'm not going to call this split. I'm actually going to do the split myself. I'm going to do that. I'm going to call this, I'm just going to call it sort. Where I was building to here was sort, but I'm just going to call this function sort. And I'm going to say, let's see, node ptr head, and it could change the head pointer, so I do head, and then int pivot. I want to try writing a sorting algorithm. This is something that you'd see in a second-year course. You sometimes see it in certain first-year courses, but what I want to do is this. I've now discovered that if I want to, I can split up a list based on a pivot value, the pivot being used to decide which nodes go where. So I do 6, 10, 17, 111, -1, 187. And now suppose that I choose 10 as my pivot. So I choose 10 as my pivot, and then what I do is I break this thing up into two lists, one that is all the elements that are less than 10, so that would be 6 and then -1, and one is all the elements that are greater than 10. So 10, 17, 111, -1, 187. Now suppose that I try doing the same thing again. And notice how this time, the first time I chose the first element to be my pivot. Let's suppose I do that again. I try splitting the list 6 into elements that are less than the pivot and elements that are greater than or equal to the pivot. Now they're -1 and 6. Suppose I now merge those two lists back together. You'll see that if I do that, then the list comes back and it's -1, 6. It's in sorted order. Suppose I do the same thing with this. Now 10 is going to be the pivot again, and so I get, oh wait, this -1 isn't supposed to be there. 10 is supposed to be the pivot again. Now if I do that, I'll notice that the split actually just puts everything in the same list. So I'm going to make one other little change here. When I split a list up, what I'm going to do is split it into things that are less than the pivot, things that are equal to the pivot, and things that are greater than the pivot. And then I should have some smaller lists when I'm done. So if I have, let's say, something like this, and then there's 4, what I'll do is I'm going to ask each of these smaller lists to sort itself. So it comes out as 4, 6, and this list stays at 17, 111. Once I'm done, if I mash all three of those lists together, so 4, 6, then 10, then 17, 1, 11, the result is the sorted version of my original list. So I can actually use this sort of partition idea as a way of sorting things. And I'm going to try doing that here. I'm going to get rid of this word pivot. Instead, I'm going to choose the pivot to be the first element of my list. So I'm going to say, well, if head is equal to a null pointer, well, in that case, sorting an empty list is easy. And I can show you how. We just do nothing. There we go. Okay, what are the other options? Well, in this case, there is at least one element. So I'll say if head arrow next is equal to a null pointer, well, that means we've got a list of length 1. Okay, so sorting a list of length 1 is easy. And I can show you how. We just do nothing. Okay, what else? Well, otherwise, I'm going to split my list up. I'm going to say int pivot equals head arrow element. All right, so the idea is I'm going to choose something to divide my list into several different pieces. I am now going to basically just grab this entire piece of code. And I'm going to bring it down. What I'm not going to grab is the part that splices the lists back together. I'm going to use that eventually, but not just yet. Okay, so I'm going to paste this whole thing in. Wow, that was not what I copied. Let's try it again. I'm going to go grab this. I'm going to hit the copy button. Maybe my keyboard is failing. I don't know why I can't copy things. Okay, I'm going to paste this whole thing in. I'm going to make a couple of little modifications. I'm going to get rid of my C-style initialization here. And I'm going to now have 3 lists. I'm going to have one list of things that are less, one list of things that are greater. So I'm going to call this greater instead of GEQ, and one list of things that are equal. So I've got greater head and greater tail. So I'll do greater head, greater head. There's okay, I think that takes care of all of that adaptation. And I want to do one more thing, which is add another list. So I want to partition my list into 3 pieces: the greater than piece, the equal piece, and the less than piece. And so I need an equal list for this. Now, the reason you might ask, why would I need a whole list just for the pivot? So my idea is I've got this list. Notice how it might contain duplicates. And I split into 3 pieces. The piece of things, and my pivot is 10. The piece of things that are less than 10, so that's 6 and 4. Then the set of things that are equal. This could be a whole list of things. There could be lots of 10s in my original list. And then the set of things that are greater. My idea is I split them, I sort them, because maybe I've got some way of sorting a list of things, and then once they're all sorted, I join them all together in order. So first the less than list, then the equal list, then the greater list. And when I'm done, I'll have so let's sort this one. When I'm done, I'll have a sorted version of my original list. Okay, so for this I'm going to need node ptr equal head, and that's null pointer, and then node ptr equal tail, and that's null pointer. And then I'm going to adjust my partition code a little bit. So I'm going to say if the element is less than the pivot, then I add it to the less list. Else, if the node arrow element is equal to the pivot, then I'm going to add it to my equal list. And then a final else is adding it to the greater list. That's the only remaining case. So to add it to the equal list, I'm just going to steal the code that I used to add it to any other list and adjust it. So add it to the equal list, the equal list, equal list. And so we do equal head. And equal tail. And I think that's all I need for my partition. So here's the less than list being formed. Here is the equal list being formed. And here's the greater list. And now what I'm going to do is I've got 3 completely separate linked lists. And I've got this function that is purporting, at least, to sort a linked list. And I think, hey, I've got 3 slightly smaller linked lists. Although I guess I don't need to sort the list full of elements that are equal to the pivot, because they're all going to be exactly the same, and therefore that list is already in sorted order. I'm going to call my sort function on my sublists. Oops, sort. Now, by doing this, there's a certain thing I have to be careful of here, which is that if I'm sorting, if I've got this list of things that are less than my pivot, So I don't know, 6, 4, 9, 7. Well, as far as I know, if this is my less than list, here's the head, it's this node, and here's the tail, it's this node. And the sort function will probably modify the head of my list because I'm giving it the head, so it can modify that. But if I have a tail pointer, that's going to become irrelevant. I should never use that again because that could be changed. It's no longer going to point to the real end of the list. So what I'm going to do now is I'm going to walk along less, equal, and greater lists and add each node to the to one large list with the original head pointer. Okay, so head equals null PTR. And now I'm going to just write separate loops to iterate through each of my sublists. So while node PTR node starts at less head, node is not equal to null PTR, node equals node arrow next. I have two cases, or I could use a clever pointer trick, but I will not do the pointer trick. I'll just have two cases. The two cases are if head is equal to the null pointer, well then I'm adding the very first node. So I'll say head equals node, just like last time. Just like in my partition loop, I'm going to need to use a while loop for this because I'm going to be reconfiguring the nodes as I go. So I'm going to write node PTR node, and actually I think I already have a variable called node, don't I? I do. So I'm going to say just node equals here. So just like before, I'm going to be walking along each list and rearranging the list based on what I see. So I have to keep track. I have to make sure not to lose a pointer to something. So instead, I'll do the same trick I did. I talked about this earlier in the video. I'm going to save a copy of the next pointer. So I'm going to say node PTR next node, and that's going to be equal to node arrow next. And then at the end of my loop, to get us back on track, I'm going to say node equals next node. That way I can do whatever I want to my current node. I can manipulate its pointers all I want, and I shouldn't have a problem. Okay, so if the head equals a null pointer, then head is now going to be my the new node the node I'm adding becomes the head of my list. Otherwise, I've got this list that I'm building up. And it's got at least one element in it. And I've got this node that I want to splice into the list. So I guess I need a pointer to the last node in my current list. So I'm going to make a tail pointer for my big list. So I'm going to say node PTR tail, just the word tail by itself, not less or greater. And it's going to start out as null pointer. And I'll say, okay, so if when I add the very first node, then head and tail both equal node. Otherwise, tail arrow next equals node, and then tail equals node, and then node arrow next equals, I can put the node arrow next below the if statement. So I add the node to the list, I set its next pointer to null, but don't worry, I've saved a copy of what it previously pointed to so I can wrap around and do that again. Now, I'm going to do this for the less list. I'm going to do it again for the equal list, so that would be equal head. And I'm going to do it one last time for the greater list. And I'm going to just try testing this. I've written a lot of code without testing it here, so if it doesn't work, then, you know, I sort of know whose fault that is. I haven't actually called my sort function, so I'll call sort, and I'll give it the head pointer to my big list. Now, if this doesn't work, it probably is going to crash. It's unlikely that it would not work in a way that doesn't just, or do nothing. But I take a look at it, and it looks like I take all my elements in an effectively arbitrary order, although there are some large, let's move some of these small elements to higher up in the list. I take all of my elements in an effectively arbitrary order, and I look at them when they come out, and they are now sorted. The algorithm I have just written, which is a lot of code, but not very much work, because you'll notice it's just a while loop, and then a recursive call to sort the less list and the greater list, followed by 3 more while loops. It's long, but it doesn't. There's no nested loops. There is this recursive call in here, and it is a lot of code to write, but it does actually probably work pretty fast. In fact, it's so fast that the name of this algorithm, this particular sorting algorithm, is Quicksort. And you can go look it up. It's got a Wikipedia article. Quicksort is one of the, in my opinion, sort of one of the big sorting algorithms. It's not my favorite. In fact, I actually don't like Quicksort very much, so I'm sort of annoyed that I ended up writing it here. But Quicksort, because Quicksort has this relationship to partitioning, I felt like it was a nice sort of coda for this set of exercises. So I just pasted by accident. The quicksort algorithm partitions an array into 3 pieces, or in some cases 2 pieces, based on a pivot value. If the pivot value is chosen wisely, quicksort is extremely fast. If the pivot value is chosen poorly, then it's not fast. It partitions the array, it then sorts each of the pieces, which are smaller lists or smaller arrays, and then it mashes them back together. It joins them back together. And the way that I've joined them is one of several ways of doing that. And so I've written an algorithm that does sorting of linked lists without even copying the elements of the list. At no point during this algorithm does it create a new node. All it does is rearrange the pointers on nodes that already exist and keep a few pointers of its own to do all of its bookkeeping. So although it's tedious, it actually doesn't require using that much more memory, besides the memory I need for the variables and all those recursive calls. We'll do one more test case. Let's delete some elements and see what happens. Okay, so we've got this. Let's delete more elements. See what happens here. Yep, okay, it looks like it works. Let's make sure that we can actually sort lists of length 1. All right, I think we're good. So we've got ChatGPT's 3 exercises, which were fine, and a lot of them were sort of similar to each other. I get one of them was basic, the next few were similar, but that partition thing at the end had a silver lining, which is we got to write this sorting algorithm.